I'll start again. Let me begin with a word of prayer. Everybody's here is here. Safe to say. Dear Father, we thank you for this day. We thank you that the CFAWs are gone. Help us to enjoy this class together and to prepare for the test, which is soon coming, Lord. In your name I pray. Amen. What? Am I the only one? Annoying little punks? No, sorry.
Does CFAW directly influence you that much?
Not really. There's just a certain madness that descends upon the campus, right? It's like palpable, nervous, adolescent energy. And then the CFAW gets here. No, sorry. Yeah, it's very classy, right? Anyway, so this is where we are. Test 3, today's discussion. We have talked about rings and integral domains, ideals, factor rings, prime and maximal ideals. We've talked about ring homomorphism, the field of fractions, polynomials, how to factor polynomials, although you already knew that. Various divisibility theorems, extension fields, and finally algebraic extensions. So, and then of course you have 2 homeworks which reflect those ideas, right? Mission 6. Is there anything in Mission 6 you guys would like to talk about? Mission 7 is more vexing to you?
I have one question.
What? Yeah.
59.
59.
59 was the question that you said we did not know how to do.
Yeah, we still don't know, because to answer 59, we need to have much more understanding of what finite fields look like. We just don't know that yet. That would be a 422 question. Yeah. So, yeah. No, I'd have to change it significantly to make it a reasonable question. Other questions? So mission 7 then? All right. Past tests. That's a good question. That would be ideal. Ha. Ha. Very funny. Let's see here. Let's see, here's the course page. Oh, look at that. I have the statement of test 3. Oh, I'll just make sure you... Maybe I thought the students needed to practice it twice. It seems more likely I just cut and pasted and forgot what I was doing, in all likelihood. So this is the test I gave in fall of 16. Question 1. Question 1 basically says, hey, it's an integral domain, prove cancellation. And of course I had some subset of the students tell me it's an integral domain, so it's got cancellation. Yeah, right. Yeah, it's like, I don't know. I don't even know what to say about that. I'm clairvoyant. What can I tell you? So, so here's a set. I claim it's an ideal. And I say, prove it's an ideal. So you got to check the subring test and the RNG test, rather, and the Uber closure, right? See here. Problem 3, let R be 3 comma x where x is in the natural numbers. Prove that either R is 3 or R is z. So that's interesting. That looks like something that you could do on a test even though you hadn't seen it in homework. Here you're asked to prove that the product of x plus a and y plus a defines a well-defined operation on the set of cosets. So there's that. Give an example of a field with 25 elements. How would you guys do that? Any ideas? For you guys, I think that would be a challenge question. Although, well, no, we did look at what? We looked at z2 of x mod x squared plus x plus 1. That gave us a field with 4 elements because z2 times, two z2 parameters gives us. So what I would be looking for would be an irreducible quadratic over z5. So that z5x mod that irreducible quadratic would give me 2 parameters, a and b, ranging from over z5. That would give me a field with 5 elements. If we could find an irreducible quadratic in z5. Oh, that would be a reasonable question for you guys. You had a homework problem where you actually figured out which quadratics in z5 of the form x squared plus a were irreducible. Did you not? Yeah. Is that a field? No, it is not. Because x squared minus 3 is not irreducible. X squared minus 3 factors into x plus root 3 times x minus root 3. What's the context here? Reals. Yeah, context matters. Now, you would have been right, probably for the right reasons, possibly, if I changed the R to a Q. Yeah. That was either a strange sneeze or an attempt to redeem. Show that this is algebraic over R. Well, that's not too hard. What you got to do is isolate the radical, square it. Isolate the radical again, square it. You'll get a quartic, which takes this as a 0, right? Which then shows that there exists a polynomial which makes it 0, which is to say that it's algebraic, right? Show that the following polynomials are irreducible over Q. Eisenstein. P equals to 5. Irreducible. This one, x cubed plus x plus 1. Where was the context? Oh, well, that's an interesting one, isn't it? Huh. Well, I don't know. I have to look at the solution for that one. I'm not sure what was the intent there. Find the degree of that over Q. It's degree 5. And the basis is 1 alpha alpha squared alpha cubed alpha to the 4th. Like so. We'll look at the solution to this in just a second.
I think the solution for 8, I was looking at it earlier, I think you did approach it with a mod 2. But could be wrong. I remember it didn't make a lot of sense to me at the time. That's about it.
At least we didn't get rickrolled. Let's see here. Remember we have a theorem, right? If you can show that the polynomial is irreducible, what theorem am I using here? Let me go back to the notes and find it. I believe I was using Theorem 4.6.13, which says what? It says if you have p's prime and you have polynomial degree, whatever, non-constant polynomial, right? And if we look at the reduction of the polynomial mod p, then if the reduction is reducible, rather irreducible over zp, and the degrees are equal, then it's irreducible over q. Okay, so what I'm doing in the solution to that test problem is I'm looking at the reduction mod 2. If I can show it's irreducible mod 2, then it implies it's irreducible over the integers, right? And if it's irreducible over the integers, then what? Okay, let's see here. Curses. Where was I? Oh, yes. Where was I actually? Over here, right? Oh, so this is over Q, right? And the theorem before that said it was, there's a connection between irreducibility over Q and over Z. What was the connection? I think a polynomial, an integer, a polynomial with coefficients from the integers is what? What's the result? Oh man, I gotta go back to the notes again. Well, yes, but before that, I said that if we have, if it was reducible over Q, then it's reducible over Z. Let's see here. Nah. So so my question for you guys is, what's the connection between potential irreducibility of a given polynomial over the integers versus irreducibility of a given polynomial over the rational numbers? If a function, if a polynomial is irreducible over the rationals, does that imply that it's irreducible over the integers? Right? What about the other way around? If it's irreducible over the integers, does it imply irreducible? No. We can think about like 2x plus 4 is reducible. Well, excuse me. Oh, let me shut up. Anyway, getting back to this one, so what I've done is I've proved that if we look at the reduction mod 2, we get 1 for both, which shows you that this cubic is irreducible because it has no zeros, right? If no zeros, quadratic or cubic, we have irreducible, right? So this is irreducible mod 2, and then that implies irreducible over the integers, and hence the rationals, right? I think irreducibility in the integers implies irreducibility in over the rationals. Is that fair? Can we prove it? Let's try to prove it, if it's not too horrible. Because you guys don't seem to be very certain of what I'm saying. So what would it mean if we had, so let's suppose f of x in q of x is irreducible, right? So my question, right, is f of x in z of x also irreducible? And so here I'm supposing that this happens to also be what? It happens to be a polynomial with integer coefficients, so this question makes sense, right? Generally speaking, you can't compare these two because rational coefficients are not integer coefficients, generally speaking, right? But suppose that you're looking at the case that they are. So suppose this is irreducible. Look at it in z. what would happen if you supposed you had a reduction over here? What would that say? Suppose you did have a reduction over the integers. What would that? Why would that be problematic, given our assumption that it's irreducible over Q? Right? Because A of x and B of x would also be polynomials in over Z. I mean, excuse me, over Q, right? So if they're in Z of x is a proper subset, right? Of this, right? And so you'd have a reduction. I guess the thing I got to worry about is the 2, right? Like what if this is 2 times A of x, right? Or 2 times B of x. What if A is like 2? I guess we got to worry a little bit, don't we? Because when that could be a reduction in Z, right? Because 2 is not a unit. And yet that would not count as a reduction over Q, right? So it seems like we do have something to worry about. Why is that not an issue for this x cubed plus x plus 1? I mean, it's monic, right? So we can't factor out something like a 2. If there is a factorization of x cubed plus x plus 1 over Q, I mean, if there was a factorization of x cubed plus x plus 1 over Z, rather, it would necessarily also be a factorization over Q, because we couldn't have a factor which was a unit that was not a unit in Z, but yet was a unit in Q, I believe. I think there may be a theorem in the notes I'm neglecting here at the moment. Let's go back and look at that section a little bit more carefully. If it's reducible over Q, then it's reducible over Z. Yeah, okay.
That just implies that if it's irreducible over Z, then it's irreducible over Q. It's admittedly a long way, but I feel like that's just
Mm-hmm.
the case.
So you think that theorem 4.6.1, if we turn it around, because irreducible means not reducible.
Right.
So if a polynomial is not reducible over Z, and that implies it's not reducible over Q? Okay.
It implies B not to be a plus not
What's that called?
a. I cannot remember.
Yeah, contrapositive. There we go. So as an example, while we're talking about irreducibility, which is admittedly a picky issue, probably the pickiest thing on this test, honestly. You know, this example is very troubling, right? If x to the fourth plus 1, we can show it's reducible for any prime p, and yet it's irreducible over q. So that's not to say that we can't prove irreducibility for some polynomials, just not for this one. For the one on the test, we can prove irreducibility of, on the 2016 test, right? We have proved irreducibility. This one here, x cubed plus x plus 1. So I would point out that what I've proved here to be, I think directly from the theorem I've proved that it's irreducible over z. Then you're saying that the contrapositive of the theorem in the notes says that irreducible over z implies irreducible over q? But what I'm fussing about on the board is irreducible over q, not implying irreducible over z. So we're not saying different things. I'm picking at something that's irrelevant to the question. Yeah, but is relevant to your thinking, yes. So again, the irreducible theorem in the notes says that if we can show it's irreducible mod p, that implies irreducible over z. Do you guys get why that is? Do you understand that sort of on a macroscopic level? What does it mean if the reduction of the polynomial mod some prime is non-zero? That means that if you plug in the equivalence class, anything in the equivalence class into the polynomial, right, from a given equivalence class, it spits out the equivalence class which does not contain 0. And if you can do that for every equivalence class, that means there's no possible integer which when you plug into the polynomial, it goes back to the 0. Right? Now, if you could plug in a quadratic integer somewhere into the polynomial and get 0, get the equivalence class containing 0, that doesn't prove that it actually has an integer 0. It just means it's possible. But when we plug in the equivalence classes, we don't even get the equivalence class containing 0. That means that 0 is not a possible output for the polynomial for all possible inputs, which is to say that the 0 cannot be factored over the integers. So, and what's neat is that theorem is not limited to what? Is that theorem limited to degree 2 or 3? No. And how was that proved? You're like, how would we know? You didn't do it in class, right? We expect me to read the notes? Yeah, ideally, that would happen. But the proof is in terms of this, primitive polynomial content business and so forth. Not this one, but oh, phooey. Where do we go? Where'd that stupid thing go? Ah! I'll eventually find it, guys. So good point. We should take the contrapositive of theorem 4.6.11. That'd be useful for our thinking. And we should also keep this one in mind. This is the other big gun in addition to Eisenstein, this reduction theorem. But you notice there's just the assumption that it's non-constant, right? And also that the degree of the reduction has to match the degree of the original polynomial. But other than that, this is a beastly theorem which has vast application. You should know what it says and how to use it. Okay, enough about that. Let's go back to mission 7. Wait a minute, no. Where were we? Test. You guys got me started on the test. Oh, where am I? Oh, yeah, the solutions. That's fine. I'll get to it. We might as well do it this way. So here, yeah, obviously this takes that as a 0. And then the question is, okay, well, that's great, but that doesn't prove that this is the irreducible polynomial until, I mean, it doesn't prove that that's the minimal polynomial, if you will. So the minimal polynomial is the irreducible polynomial, which takes that number as its 0. So it's the polynomial of least degree, which takes the fifth root of 2 as a 0 with rational coefficients, right? That would be the so-called minimal polynomial of alpha, as I've labeled it here, over Q. I don't think I've called it the minimal polynomial in class before. Shame on me. But this is called the minimal polynomial of alpha over Q. Because I've just been calling it that polynomial, right? Which is kind of silly. We should give it a name, right? I mean, we need to show that the minimal polynomial is irreducible, is the thing I'm trying to get at. But here, that's easy, because Eisenstein with p equals to 2 does it for us. It's kind of, oh, okay. And then, so if it's irreducible, then that makes this a field with basis like so. There you go. What's this here? Let R be a commutative ring with unity, A an ideal of R. Prove the quotient ring is an integral domain if and only if A is a prime ideal. Yep.
I have a question about the last problem.
Oh, okay.
If it was brackets.
The last, like this one?
Yeah. So like if it was brackets instead of parentheses, what would that be?
That would be the ring formed by adjoining alpha and looking at rational coefficients of alpha and powers of alpha. It'd be the same thing. But in this context, it's a field, of course. It's essentially the same discussion we already had about Q adjoining the square root of 2 versus Q adjoining the square root of 2, brackets versus parentheses. Like any way you slice it, you've got a field. So you've got the smallest field, which contains the rationals and the square root of 2. Likewise here, once you've adjoined alpha and multiplicative consequences of it, in other words, like alpha squared, alpha cubed, and rational linear combinations of those, you've already got the smallest field, which contains both Q and alpha, which is also this. Yeah. But we know it's this because of our basis theorem that, you know, if we have a irreducible polynomial of degree n, right, over f, then the fx mod the ideal generated by that polynomial gives us a vector space of dimension n over the field with the basis taken to be 1 alpha alpha to the n minus 1, where alpha is a 0 of that polynomial. All of that assumes, of course, that the polynomial is irreducible. If the polynomial is not irreducible, then when we look at the quotient, we don't get a field, a la problem 70. Or x squared minus 3 earlier on this test. Right? Where was it? Where'd you go? Yeah, problem 6, right? So this, if you look at that times that, you get that, which is 0. So there's 0 divisors, which shows you that this is not a field. Fields don't have 0 divisors. And that's because, I mean, x squared minus 3 is not irreducible. And yet, this quotient is still essentially R2 as a vector space, right? It's got two real parameters. The basis is essentially 1 comma alpha, where alpha is equal to, you know, x plus this guy, right? All right. Is there anything later in this test we should talk about? So my point to you guys would be that problem 10 is an entirely anticipatable, not surprising proof question to be asked. If you look at it, there are really, what are the two, maybe there's 3 sort of obvious proof questions that I might ask that are kind of, they've got a lot to them, but they're kind of central ideas. I would say that those 3 that stick out to me right off the top of my head would be the this one, right? The prime ideal if and only if the quotient is an integral domain. How about the other one? Maximal ideal if and only if the quotient's a field, right? And I would say the third one that comes to mind is proving that a Euclidean domain is a PID. either in the context of polynomials or in the context of a normed, of just an abstract norm. I'm sure there are other things, but those three in particular kind of stick out, don't they? Problem 11, let F be a field, suppose P of X is irreducible. Oh, look, so here I decided to just do, well, this is another thing that is a likely test question, right? Which is the connection between irreducible polynomials and maximal ideal. So that's also kind of at the same level of results that you ought to be able to prove. So we worked this one out as well. As a general rule of thumb, if I've spent 20, 30 minutes of class or something working through a proof, there is a chance that I might put it on the test, right? Oh, and here's that one. So in the absence of color, I use symbols. So 1 plus 2i, what I do? Like 0 is what? 0, so like dots for the original one. And then what I do? Asterisks for, who cares? Anyway, I would advise you, bring some colored pencils, right? Or something for this test in case I ask this question. Because your life is so much better if you've got a color option for this solution, right? You don't want to be doing this garbage, do you? It's suboptimal, right? Ooh, look, the Cayley table. And I'm showing, in fact, that it's isomorphic to apparently U5. Sorry, so slanted. Ooh, look at this. Well, that's interesting. Q of X to QQ. And defined by F of X is the evaluation at 1 and the evaluation at -1. I give you that it's a ring homomorphism. I say show it's a surjection, calculate the kernel, and decide if the kernel is a prime ideal. Huh. So I guess the question is, well, is QQ an integral domain? No, so it's not a prime ideal. Because, well, what's the image, though? Oh, come on, surely the image is everything, isn't it? I guess I have to work on it. Oh. Apparently it is surjective, and the point is that QQ is not an integral domain because it's got 0 divisors. So by the first isomorphism theorem, Q of X mod the kernel is isomorphic to the image, which is Q cross Q. The image being not an integral domain implies that the kernel is not prime, right? Because the quotient of Q of X by the kernel gives us something that's not an integral domain, hence the kernel is not a prime ideal. So this quotient by, these two quotient theorems we have, that quotient by a prime ideal gives us an integral domain, quotient by a maximal ideal gives us a field. I hope you haven't missed them because they're important. I would be negligent as a professor if I did not test on these, right? These have to be part of the test. Like that much I can tell you, right? What else seems very likely? It seems very likely I ask you to test something being an ideal or not, right? You should be ready to test whether or not something's an ideal. Whether or not something's a sub-RNG or a subring. What's the difference between being a sub-RNG versus being a subring? Right, a subrung does not have an identity. Whereas the subring does. An ideal, is it a subrung or a subring? Subrung, right. It's not wrong what you said. Sorry, it's horrible. I should stop. Let's go back to mission 7. Any questions about mission 7? Yeah. I mean, other things are important, like the field of fractions, right? Like I want you to understand that idea. And it wouldn't be impolite for me to ask you to verify something there, but if I was to do that, I would like recreate the construction of it and ask you to go from there, I don't really expect you to memorize all of that, yeah.
So with problem 7,
Oh, yes, problem 7.
Is there, I guess this isn't necessarily relate directly to the test, but just like, what is that testing when you ask a problem like problem 70, where we have to construct our own, ring homomorphism or whatever, construct something that's an isomorphism. So like, how should we, I guess, go about that?
Right, well, this is one of the problems that's in front of us. Before, when we were talking about groups, we had the problem of how do you construct an isomorphism of groups, right? And so the answer there was, well, we need to preserve relations, right? So if you can find a generator's relations presentation of your groups that you think are isomorphic, if you can map corresponding generators to corresponding generators, then you're off to the races, right? Especially if it's like cyclic to cyclic or something. For a ring, if you're trying to construct a ring homomorphism, it's even better in some sense, because you know that 1 has to map to 1, right? But you also know it has to be additive. And if there's something special in the ring, right, if there's some kind of linear combination, some sort of polynomial of ring elements which has to be sent to 0, then whatever defines your isomorphism must, maintain that polynomial being 0 in the image, because of the usual additive and multiplicative rules for homomorphisms. Like the polynomial, the image of a polynomial is the same polynomial of the images, is my point. So these comments make the structure of ring homomorphisms very limited. So you can use these things to basically calculate a ring homomorphism often. So now there is a jump, and the jump you guys might not have even noticed. Well, how would you notice yet? I haven't posted solution, but I'll explain. So that was my thought process here. Is 1 has to map to 1, alpha has to map to CD, where this alpha has a certain pattern. It satisfies alpha squared minus 3 alpha plus 2 being 0, right? So that forces both C and D to actually satisfy the same polynomials, being 0. And as such, because and I also know that I can't let psi of alpha be proportional to psi of 1, because if I did, then that would imply that the kernel of psi had something non-zero. Whenever we talk about the kernel of a ring homomorphism, what kind of kernel are we talking about? Additive or multiplicative? Additive. I hope you noticed that. If you're like me and you somehow got to a test and then had a moment of like, wait a minute, which kernel? It could be bad. Don't be that. I mean, it's additive kernel. The reason being, we're again going back to the fact that every ring homomorphism is first a homomorphism of the underlying abelian group of the ring, right? So with that identification, we have all of the familiar group theoretic results about injectivity from vanishing kernel. Anyway, so here, I need these both to be 0, and I also need that CD is not proportional to 1, 1. So that means I can't make both C and D be equal. So either C is 1 and D is 2, or C is 2 and D is 1. And since I didn't say find all ring homomorphisms, right? Or ring isomorphisms, I should say. I just chose a path. Now, even so, you might wonder, have you really proved that these are all ring isomorphisms if I was to chase down this one or that one? Is that all the isomorphisms possible between my quotient ring and R cross R? The answer is yes. But that's harder to prove. And that I wouldn't ask you on the test yet, because it's something we haven't quite got into. But that ultimately stems from the fact that I can pull real constants out of such a homomorphism. This is something, at this point we're just guessing. I'm constructing it. I'm not saying that this is a property of all ring homomorphisms, but it is in fact a property you can prove has to hold true for the kind of ring homomorphisms we're looking at. Again, that's not obvious. There's some analysis here, something kind of deep and a little bit technical. pull the A and B out. But in fact, that is something you can do for an arbitrary ring homomorphism, which essentially is what is needed to prove that the one I write down and the other one that would be from chasing the other solution are in fact the only two isomorphisms possible. But there it is. So, and then once you have that, then you can go back and answer A, B, and C with relative ease. I haven't written that part out yet, but hopefully I will sometime soon. Now, let's go back. Any questions? So I can tell you what I'm pretty sure the answer is. There are no nilpotent elements. I'm pretty sure the answer to part A is no. There's no element which has a square or a cube which is 0 and yet is non-zero. The idempotents, what do you guys think? You thought 0 and 1? That seems reasonable. I think 0 and 1 are probably the only ones. But I haven't checked yet. And then what's the other question? The units, those are just going to be the ones for which we need that it's not a zero divisor and it's not 0, so we end up needing that B is not equal to minus A and A is not equal to minus 2B. If you have, basically you have to delete two lines. Well, they're kind of more, I don't know. How am I supposed to? Here, let me draw a picture. So there's two zero divisors. There's this one and also that one. So B equals minus A, B equals minus 1 over 2 A. These and 0. These are the parts of the AB plane which do not have inverses. So everything else not on those two lines is a unit, is what we can work out. So most of this set is units, except for these two lines that are missing. But to, I don't know, get back to the heart of your question, Liam, I'm not sure I've done other examples in here, like this is supposed to be like something else we've done. I'm not sure that's actually happened for us in here. Up to this point, now there's a test. So it's conceivable there's a question on the test which is like this, and that would be a different story. But up to this point in our journey, this is not like something else. I don't think. Let's go back up a bit. I'll work my way back. 69. So 3 plus I. So you isolate I, square the thing, and you can see that alpha squared minus 6 alpha plus 9 is equal to minus 1, which suggests to me that P of x is x squared minus 6x plus 10 will do. That takes alpha as a 0 at least, right? And then I'm like, okay, but I need to show that it's irreducible, right? That shows it's a potential minimal polynomial, but is it irreducible? If it's irreducible, then bingo, it's minimal. To show it's irreducible, I suppose that I have a 0. Now, to be fussy, maybe I should use like C here instead of x, because I'm not really thinking of x as an indeterminate here. I'm thinking of it as a possible 0, right? So it'd probably be better if I put C here. C minus 3 squared plus 1 is C minus 3 squared equals minus 1. Is there any real C such that C minus 3 squared is equal to minus 1? Well, no. This is not possible for real numbers. Therefore, there is no real solution, which then, of course, implies that P of x is irreducible as a real polynomial. All right? Alternatively, you could factor it over the complexes and then give arguments which are convincing that that complex factorization cannot possibly descend to the reals. Right? How do you, there are other ways to argue this, but I think this is the cleanest. For B, again, isolate the radical, square that thing, isolate the radical again, square that thing. After a little bit, we get x to the 4th minus 10x squared plus 1, and that's a possible minimal polynomial for alpha. because it takes it as a 0. It remains to show, though, that that's irreducible. So an argument to show that x to the fourth minus 10x squared plus 1 is irreducible over q can be given. With that argument given, then we could conclude the minimal polynomial for alpha over q is x to the fourth minus 10x squared plus 1. What is that argument? Well, here's an argument. So this is Sperano's brainchild. Sperano's like, it's not too bad. You just suppose it's equal to the factorization of a pair of quadratics over the rationals. Now, to be fair, there remains the question, why isn't there a factorization into a linear times the cubic, right? That's still not addressed in my solution, but I think you could rule that out with the rational roots theorem, right? You guys know rational roots theorem? Oh, well. Let's see here. You might want to look that up. Could be useful. So if you multiply this thing out, that's supposed to be x to the fourth, obviously. Duh, G George. And then, and I still have x squared down here. Come on. Good gracious. What's wrong with me? Anyway, so suppose you do have a factorization over the rationals. Then you got this a, b, c, d that multiply out like this. And then you multiply the thing out. I somehow still have the x squared here, which is bogus. That's x to the fourth. And then when you equate coefficients of the constant, the linear, the quadratic, and the cubic coefficients, that gives you these 4 rational equations and 4 rational unknowns, nonlinear equations, mind you. Now this one's nice because that says either b and d are both 1 or b and d are both minus 1. This says that c is equal to minus a. And if you play with these for a little bit, like so, and I go in circles a little bit here, so this probably can be cut in half. You probably can cut this in half and get to a contradiction. I probably have not got to the contradiction with logical minimalism, in all likelihood. Totally likely that my contradiction proof is suboptimal. I think you probably could find a faster way to craziness. It's your goal, right? You want to get insane? Let's get nuts. So finally we get nuts down here, because eventually I get to a squared minus b minus d equals to 10. Remember, b and d are either both 1 or both minus 1, which means this is either a squared is equal to 12 or a squared is equal to 8, neither of which allow integer solutions. So that means that there's no integer factorization and consequently no rational factorization. No. Yep. So I wish that had worked out to be Eisenstein, but it just wasn't the case. Now there's another way that we could argue there, which would be to think about, we've got up here, we got square root of 2 and square root of 3, right? You could prove that this is equal to q adjoin square root of 2 minus the square root of 3. You could prove that those are equal, actually. And then, so you could view this as an extension of q adjoin the square root of 2. And, of course, this is an extension over q. This has degree 2. This has degree 2. So I think if you thought about this long enough, you can come up with an argument that the quartic has to be irreducible because q adjoin the square root of 2 square root of 3 is a field, because it's an extension of an extension, which is a field, right? But I haven't quite shown that yet. I'll try to put that in my solution. I'm still fussing with how that's best. I thought that the rational factorization was more accessible to you guys at the moment. That's why I put it in the solution, and I'll post this shortly. Now, if we go back, everything before that point is this. I showed you guys in the help session, right? So you just, or maybe you noticed it was in homework that I've already posted solutions for. I don't know. Here, Emily, is what I was talking about when I tried to do what you were doing. I actually was able to solve like the constant term, and then I could think through the linear term, but it's just like, it gets horrible. Anyway, So, don't stay up too late, be rested. There should be many questions on this test that you can do, right? Make sure you know your definitions. Definitions are lifeblood on this test, right? If you don't have a clear understanding of what's prime, what's maximal, what's irreducible, what's an associate, what's a unit, what's a ring, right? What's an ideal? It's hard to answer questions about them. So, anyway, see you guys Wednesday. Thank you very much.